Oh, what's up, everybody? Welcome back. Today I want to work on improving our custom hash map that we wrote on the last stream. So the context here is that I want to write a hash map. You would think that you would never have to do this, but I actually think it's kind of relevant here. So like we've kind of settled in Zig land on using this like memory management strategy that basically says I've got a big buffer of stuff, right? All my memory, all of my allocations, they just go in this buffer. And I'll have like a pointer sitting in here somewhere. And when I allocate some data, we'll like put the data in the buffer and we bump the pointer forwards. Huge, right? And the benefit to this approach is that I basically just never call free anymore. Fuck that shit. Right? Instead, we just keep bumping the pointer forwards, and then eventually we go, okay, I'm done with all that stuff. Don't care about any of that. Boom, pointer go back here now. Everything that was down there, freed at once. Which is like really nice when you have like trees and stuff. You no longer have to like walk your trees to free every individual little thing that you allocated. No, fuck it. You're just like, boom, don't care, everything's gone. And then also if you make a mistake anywhere down below, it doesn't really matter because you'll reclaim that memory later, right? The problem here is that sometimes in this like scratch space, we want to use a hash map, right? We want to like maybe say, I am looking at an SQLite database and I want to like count how many times these things happen, or I want to like sort these things. This has come up a couple times. You might say, why don't you just like do that in your SQL query? And I'd say, shut up, I'm not smart enough, okay? I need to do it by hand sometimes. It's just like the way it works. But yeah, like kind of like sorting stuff and counting stuff is like a thing that comes up every once in a while. And the default hash map in like Zig's standard library and most standard libraries, right? This is like the sane assumption, are like kind of like work under the assumption that you can like grow your memory, right? So they might start with some small amount of like capacity to store stuff in, right? And then they go, uh-oh, too much stuff. You've got too much stuff. Bigger now, please. Make it big, right? Get big. Oh, I lost it. Get big for me, and then I will copy this stuff in here, and then I will use this stuff now. And if I run out of room there, I'll do it again. I'll make an even bigger one and copy into there, right? But the problem is that you kind of like waste storage by doing that, because like now this stuff that I allocated here, if that's in my like linear array over here, it means that like I can't free this because we don't have free. We only have like move the pointer backwards. And so it means that like the intermediate storage is kind of wasted. In reality, I don't think this matters that much because I think that we've kind of come up with like another solution to this problem where wasting intermediate space isn't the end of the world. But I still do like the idea of only using the amount of memory that you need to use, right? I don't like the idea of just wasting all this space and like copying stuff around for no reason. So where this was eventually going to go is that instead of like resizing and copying, what if we just used like both of these buffers now? We just never free anything and we say, okay, our whole storage is now this. And then when you add more and the whole storage is now this now, right? And so to do that, we need to like implement the hash map ourselves because like the storage is like a very key implementation detail of these things. So that's kind of where we're at, is we have a hash map that uses the collision resolution of this thing is basically just like move on to the next entry of the hash map. That's what we wrote the other day. So it's like if you have like some entries in your hash map, boom, you take your key and you stick it through like your hashing function, right? Hash your key and it spits out like 3, right? So then we put like value here. Then we put like another thing there, pumps out 1, we put that value here. And then if another number in and we get 1 again, we go, oh, okay, we'll just like move forward until we find an empty slot and we put it here. That's kind of like the initial thing that we did, which I kind of, when I was like looking at hash map variants, I kind of like scrolled this Wikipedia page without like just like reading titles. And I was like, oh yeah, that seems like kind of cool, right? Because like cache locality on that is very good. But we saw a lot of collision. We saw like a lot of iterations happening where like if this thing's like relatively full, it means you have to just like keep scanning forwards forever and ever. And also when you remove elements from your list, you have to keep skipping those empty slots when you're doing lookups because it's like you're not really sure if something was there before and your thing is still in the future. Like it's hard for you to know, right? So what I wanted to try today is trying a few different like collision resolution mechanisms and seeing how they compare against each other, and maybe compare against the standard library. So we kind of like prepped our hash map to be able to like be a little bit more pluggable. We added a custom or like a sample, just like calc index no collision, just to like see make sure that like our hash map is ready to try different mechanisms. And this is like relatively successful. And so we kind of like got our thing set up to just like try different ones and see what happens. And so that's what I want to do today. So we have a little test set up where what we do is we populate a hash map by saying I want like 100 keys or something, and then like just try like generate one of those random keys like 10,000 times and just count how many times you hit each key, insert those into the map. So you get like a little histogram, right? You're like, we have some like keys here, and like you have like keys, and you might have like, you know, this key was hit this many times, this key was hit this many times, this key was hit this many times, blah, 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 right? This is just a way for us to kind of like make sure that we're doing like a lot of lookups with a few insertions, because I think that's kind of like the typical use case that I'm going to hit a lot of the time, is like, I just want to count how many times things happened. Question, wouldn't it be easier to implement a garbage collector for zig, out of scope, boom, pointer, overridden, boom? I think garbage collectors, easier by like some metric. I think complexity is relatively high. Trying to track all references to all other references, I think, is like non-trivial. I do want to write a garbage collector at some point. I think that'd be like a fun little experiment, but easier is kind of like a strong word there. I don't know if I would go that far. Okay, so we basically like hit the map in a bunch of spots, try to like count how many times we hit the map there, and then print out how many times we hit it. So if we look at like the standard library version of this thing, hold on, we need to be in release mode for this to not suck. Give me a sec. Come on, buddy. Come on. Okay. So we've kind of set this thing up so that we can like run this thing with different variants of hash maps. So if we run this guy with the standard library version, we kind of see like, okay, so the key 921246218382201971 was hit this many times. And if we run this with like our custom variant instead, so we look at like open linear, this is the same thing, we just pass open variants as open linear, you know, we see kind of like the same thing, right? 921246218138, this was like 1068, right? We're getting the same numbers. And if we compare these guys by using our favorite benchmark tool, poop, we can go like, let's compare the standard library version with the open linear version, and like, how do they compare against each other? For the same insertion removal pattern, you know, what's like the time difference? And I was actually expecting us to be like 10 times more expensive. Oh, and here we are a little bit more expensive. I suspect that this is actually a result of the debug stat collection, because I don't think it was that bad before. I don't think. When we tried this in Happy Hour, we actually saw that ours is actually faster. So I'm kind of curious why that is. Hold on, we didn't quite get this. Probably want to do like lookup stats is if enable debug stats. Hold on. This else this, and then lookup stats. Let's see, lookup stats. Does that build? Not quite, because then we have to remove this print at the end. Okay, hold on. Hold on. Give me a sec. Janet Carr. Janetta Carr? Janet Akar. Thank you for the raid. Much appreciated. I was just explaining to the guys here what the current state is of our hash map and why we're benchmarking it against standard library hash map, and we were just saying ours should be approximately as fast, even though I expected a 10 times decrease, which is not what's happening anymore. So that's kind of interesting. I wonder why that is, because I don't think that's what we were seeing. I swear to God, we were seeing ours was like sometimes faster. But whatever, I guess. We have, so we're a little slower. I don't know why it's different now. We won't acknowledge that. We won't acknowledge it. I wonder if it's because, like, the size of this thing changed, or if our print, we did maybe benchmark it without printing last time. That's the other option. Let me just check that really quick, and then after that we'll stop. We'll just admit that we're bad. Okay. We'll just one more time. Chill. Everyone, shh. We gotta let him think. Don't disturb him while he's working hard. Okay, we're slower. You know what it is? Is that we added removals to our test. So before, I think that the last time we did this benchmark, we didn't do any removals, and now we do, and that's probably just making things worse, which makes sense. That makes sense. I forgot. Okay, so we now have like a baseline, right? We have the standard library version is what we should be targeting. We're like 7% slower. Maybe that's fine. We'll chill. And so yeah, let's just try a couple of different collision resolution mechanisms and see what happens. Because I'm not convinced that what we're doing right now is sane at all. I also wanted to make sure that we're under some like reasonable load factor, right? Because like chance of collision goes up if your buffer is too small, right? If you have 100 numbers and 100 entries in your hash map, you're like very likely to collide, versus if you had like 300 entries, then like you're much less likely, right? So I wanted to start by making sure that we know what our like load factor even is. And then we can kind of size our buffer appropriately and then figure it out from there. So let's do something in here. Like we'll say in our configuration, we say like max load factor. And this is going to be like float, I guess. And this is by default null, probably, right? And what we'll do here is we need to calculate the load factor somewhere. So I guess that means that we kind of have to keep track of how many entries are populated in this thing, I guess. So here, I guess on insertion, we probably do, when we put a new entry in here, we say self size plus equals 1. And then on removal, we probably do self size minus equals 1, right? That seems kind of reasonable. And then we can just do something like, if when we insert something, if we have a config max load factor, we will calculate our current load factor. So we have size over, this is a float from int, size f is this, size, we have like capacity is float from int of key storage len. Yep. And then we return size, if size f over capacity f is greater than max, then I guess we probably just crash. Just freak the fuck out. And then we can try seeing like, so here if we set like max load factor, I guess maybe we want to write this config somewhere else. It's fine. Max load factor is, 0.5. And we make our buffer kind of small. We should start to see ourselves crash. Yeah, so here we're hitting the capacity is over the maximum. So if we then increase the size, zig build open linear. Okay, so he's chilling. So then if we're like, okay, but like, what if we wanted our max load factor to be 0.3? I assume that this will crash now. Yeah, hype. Okay, cool. So now we can have like, we at least have like an approximate idea of our load factor, which is good because now we can make like relatively reasonably good decisions. That sounds like too much, what's it called when you, like guard yourself from being wrong? Whatever that is. Okay, so let's try moving our collision resolution somewhere else. So we have a fixed capacity hash map. That was kind of the point of this thing, is that we kind of take the hash map and we say, boom, here is the amount of memory you're allowed to use. You can never go over this much. And so if we want to make our collision resolution use like a linked list, the storage for that linked list has to live somewhere, which means that we probably either have to dynamically grow our storage and like kind of like allocate half the buffer. Like we're gonna have to allocate like some amount for collision resolution, right? Or we kind of we could say that we have a buffer for typical entries and we can use like an allocator for like the remaining. That's probably nicer. That's probably nicer because it will hurt my brain less to do it this way. So let's do something like, let's take in an allocator instead. Okay. And we'll just say, capacity. So we'll call this the like normal storage capacity, the like, you know what I mean? I want a name for how much memory is this thing going to be using except for on collisions. So like key storage capacity, like a storage non-collision capacity, I guess. Okay. So then I guess we use capacity here gets replaced with a usize, and this becomes capacity here, and then I think everything else is fine. I think so. This is non-collision capacity. And then how are we gonna store this stuff? So we put like, we get the number of elements out of this guy, and we allocate the number of stuff, the things that we want. Cool. And then we store the allocator for later. Or we probably want like some form of like pool of shit. Yeah, pool of like nodes for collisions. So can we call this like collision entry? And this thing's gonna store like the key, probably, and the value, right? And we'll just like put these in collision storage. So that means that we need some sort of like collision storage. So maybe we kind of store this like this. And we'll do like no. Available collision storage. Yeah. Yeah, so this is where we'll put entries that are not currently as part of some linked list somewhere. I think that makes sense. And then I guess that means that like the storage format of everything else is going to change. I kind of feel like we need different storage types. So we're going to say like open linear storage is going to be like this. Right? And then we have to kind of use that somewhere. So we're going to be like storage, open linear storage. Okay. Let's kind of figure out how this starts to fall apart now. What the fuck is he complaining about? Expected 2 arguments found. Oh, true. True. So now we're using, map alloc is heap alloc buff allocator initialize with buff. Yeah, and then this goes in here. Yes. And then this is like this. Okay. And then we copy this somewhere else. Yes. Okay, so this is like map. I guess this is like scratch here. And then initial capacity was like 8192. Yeah, okay. Does that work now? Close. So here our open linear storage needs some sort of like init function that returns I don't know. He just does whatever we were doing before. Something like this. Something like this. Okay. Oh no, we have to calculate num elements here as well. Here we go. Yeah. There we go. What's the language server? It's just ZLS, Zig's language server. Okay, so now we can do this. And now things are going to start falling over probably when they try to use the storage. So here, we're going to have a storage like insert element, I guess. At index, probably, right? Seems kind of reasonable. Kind of reasonable. And this is going to return like key pointer and value pointer, which I assume we have something for. Maybe not. Oh, we have this entry here. So we can kind of pull this out and put it next to get report result. And then we can return an entry from insert element. Nice. Yeah. Yeah. So now this guy is kind of like... So we can have like get element and insert element, I guess. I think that these are the guys. So on get, we just return... I guess it's kind of like this no matter what, actually. Yeah. And so now we go like self storage get element of index. Here's entry key pointer. an entry value pointer. Okay, that makes sense. And then here we get the entry from here, and then we like set the stuff. So this entry is actually needs to have a mutable thing. So we can say entry key pointer is equal to key. Oh, but we also have to like in get element, I guess here we do this. Yeah. So this stuff is kind of part of that. Key pointer is equal to key. Okay, and then we return entry, key, pointer, and entry value pointer. Okay. Close. This is mad because this guy now needs to be like this, which is fine. Okay. Then this max load factor calculation, I guess, needs to come from storage len or something. We need to like implement that on this guy. Yeah. You're using close hashing? I don't know what that means, but maybe. Okay. I think this is open. No? I think open is the one. Open addressing. Maybe I am using closed. Maybe I used the wrong word. Open addressing, where every entry record is stored in the bucket array itself. No, that's what this is. This is open. Closed is where you go somewhere else. I don't know, man. Names are hard. Okay, so now we have, like, I hope, a semi-generic storage that we can start swapping out in a second. Oh yeah, I guess this guy needs to implement remove as well. So this just does this. Boom. And then here we call self-storage remove element on index. Okay. Are we there? Almost. Storage len. Oh, this iterator is probably dependent on the storage type, huh? Probably. Iterators are going to be implemented differently if we're using a linked list, so this guy gets like an iterator. The iterator moves into the storage. You know, so like this stuff kind of moves into here, into the storage section, and then this just, our iterator function is like, you know, type of self-storage dot iterator or something like this. Yeah. That seems kind of close. He doesn't like this. Parent should get like this. This guy needs to have the right type here. Open addressing means closed hashing. Oh, I see. Okay, calc IDX linear or open linear. This guy can just use storage directly because it should only be called when the storage is our expected storage type, which is fine. Maybe this should move into the storage thing, but whatever. Now he's whoa. No module named stud? I guess I thought that we had that thing and we don't. No, we do. It's right here. No? Oh, here. My bad. Okay, so building looks like it's working, which means that we should be able to run. No, he's still mad. Self value storage at 183. God damn it. So this should be, we calculate the index. If the thing exists, then we should be able to call self storage get element index value pointer. Yep. That should be fine. That should be fine. Anyone else? Expected 2 arguments, found 1 at 473. God damn it, we're getting close. Scratch allocator. And what was the number here? It was just like the full area, so like 1 times 1024 times 1024. Oh my god, 263, we're getting so close. We're so close. Okay. So this guy uses the same storage, I guess, which is fair. So the storage name is gonna have to change probably, but we're finally fucking there. And so can we just make sure that like we didn't break anything by doing that? We're good. Everything still works. And so now we should be able to swap out the storage for somewhere else, for something else. So let's actually call this, well, this is a bad name. We'll call this like linear tomb storage or something. It's linear storage with tombstones to mark that the thing is to mark that we're using like, oh, the skip on get should be called tombstone, but it's like we have used entries before. KPTXZZ, thank you for the prime, much appreciated. Okay, so now that that's out of the way, we can now swap our storage format for linked list storage, right? So this guy's gonna have to implement like the same interface here. So what I'm gonna do is I think I'm just gonna copy all of these guys out and then just like delete their contents, right? And we'll figure it out in a second. Okay, so linked list storage. So we said we're gonna have some sort of like initial capacity, which I think means that key and value storage, I think is still correct. I think. I think what we're gonna do is, but we don't have this like valid thing to keep track of. I think we do. We have valid, just no tombstone. I think. So here, because we need to track if this guy has something in him or not. Yes. And then, so that means that we have to calculate how many elements we can fit in the capacity they give us, which means that this function is going to be kind of like based off of which version, like what our storage is like. So this guy says, let me calculate for linear tomb storage, and we're going to have like a very similar calculation here, except we don't have the second tombstone bit set, which means that this 2 from last time turns into a 1. I'm like almost positive of that. 1 and 1, yeah, pretty sure. We'll see if we fall over later, but that's fine. So then we are going to allocate key storage and value storage and valid storage, but not tombstone storage. We don't need that shit. Okay? Uh-huh. Okay. Now, get element. This is using an index here, which I think is maybe wrong. Maybe, because if we're trying to get like a specific element here, this is actually like, our indexes might point to lists, right? Which means that key is also kind of wrong here. No? Like, so at every entry in the key storage, we are going to either be, I guess it's kind of more like storage. And each entry in the storage is either going to be, let me think for a second. Where is this going to go? Where's it going to go? We haven't got here yet. So if I come in and I say hey, I want to store my thing in the linked list normally. Smiley face, right? He goes here. But then, like, we have a collision. And so now this guy needs to. Maybe he doesn't store the smiley face anymore, right? Maybe he stores a pointer to the list. Yeah. So that means that, like. Yeah. So this guy. Um. We can probably. How do we do this? Uh. So this is going to be a key element is going to be like a union of either uh he's either going to be a pointer, which is going to point to some sort of like key value thing, right? So it's going to be like linked list entry. You know, which is going to be like next, or we're going to have key, we're going to have key here and value, right? Yes. Then we have another option, which is like entry, right? And this is just a key. And then in Zig, like, I don't want like the enum. I don't want like the union to store the enum. I want it to be like out of band. So I don't know if you can do that in Zig. Untagged unions. Like I want the opposite of a tagged union. When should I use untagged unions? How do I do that? Untagged unions, external union. Yeah, that's what I want. That's what I want. You can remove the enum from the union, but then like it doesn't like. I think that this doesn't work this way, does it not? Maybe I'm confused. Zig language reference. Union. So there is a bare union defines a set of possible types. Only one field can be active at a time. The in-memory representation of bare unions is not guaranteed. Bare unions cannot be used to reinterpret memory. For that, use pointer cast or use extern union or packed union, which have guaranteed in-memory layout. Yeah, okay. Okay. And then here, access of union field. Well, but here they are tagging it still, which I don't really want. Right? They're doing like the checks. So I think I want like extern union. Which is fine, yeah. Let's do that. Okay, and so now what we need is oops, I guess these are kind of known things now, which means that here we also need to delete these. Key storage is key elem. And then how many bits of information do we need for this? We need to know if it's a pointer to a linked list or a key or a invalid. So like I wonder if we have to do it like this. Like, you know? I guess maybe, right? Where you have like Key, like entry, pointer, or invalid or something. I guess this is kind of what I want, huh? It would be cool if we could like force this to pack, but I don't know if that's that trivial. I don't know how easy that is. Like, I don't know if you can do like, that type of shit, or even if you would want that. So we can figure this out later. I wonder if there's like stood, like packed array or something. Also seems like the type of thing that would exist. But for now, let's just do this, and we'll see. We'll kind of loop back later. Fix me, maybe pack these a little closer for cache. Brevity. Maybe that's the wrong word, but it's close enough. Okay. So now we should be able to do something like, I guess this num element calculation is wrong now. So we kind of need to do like, we're looking at key elem, value, and key tag. So now we have like a tag size is size of key tag. And we need like, this is now key size times n plus value size times n plus tag size times n is equal to buff length. And then we have to do the algebra to convert this into n. So we pull n out. Key size plus value size plus tag size is equal to buff len. And so it's just buff len over that. Yep. Easy. Easy. Okay, so we calculate the number of elements. We allocate our tag storage like this. And this is key tag here. Nice. So we have key storage, value storage, and tag storage is tag storage. All right. Cool. So now what? On get element now, this doesn't feel like it makes sense, right? Using an index here is wrong. Maybe. So I feel like this, it's almost like get here is implemented by storage, or get or put is implemented by storage. Get and get or put? That seems kind of reasonable. Seems kind of reasonable. So it's almost like this calc index, like almost all of this moves into storage. That makes sense. All of this moves into storage. Boom. Calc index, depending on the config. And then also like this just turns into like get and get or put and remove. So this is like based off of the hash. Yeah, that feels kind of right. And this returns an entry. And then we have get or put as well. Yeah. Yeah. And then we just kind of like shuffle this shit around. So get or put here implements this. And this is no longer, like, we have calc index based off of the key. So it's like almost like the hash is moved up, I think. I don't know. Then this is like we take the hash and go over our storage length. Pipe. Maybe it's key hash because it's colliding. Nice. Nice. We're getting closer. Calc index no collision takes in index now. I guess. I don't know what the fuck is going on here, but these are the names that we used. Okay. Oh, and we also do need the key here, true. We do need the key here as well. Can't get away from that. Okay. Cool. We'll see where this goes. Things are definitely falling the fuck over. Like, things are getting complicated. They're getting complicated, but that's okay. It's okay. We'll get through it. Let's just comment out this linked list storage completely right now and try to get this thing building again. Now that we've kind of changed shit. So this is key hash because there's a collision and we need the key as well. Key and key hash. That's calculated externally. So on get or put, we're calling get element with index. Okay. Oh, because we're calling calc index here with key, hash, and key. Okay, there we go. There we go. And then on get, we must be doing something very similar. Uh-huh. This guy wants key, hash, then key. And then this turns into storage get. Nice. Something like this. Maybe like this. And then we figure it out down here. Entry is this. Okay. We get our entry. And then return entry value pointer. Or else return null. Yes. We don't have the entry here. Then we return the value pointer. Everyone's happy. Okay. This is entry is storage get or put with key self hash key. Nice. And this is probably tried. And then we return the conversion of this thing. No. This guy just has to return a get or put result directly. He has to. Because he's the one who knows. Okay. Jesus. We're getting somewhere. We're getting somewhere. This is mad because num elms, he's passing in too much shit. This is mad because self hash doesn't exist yet. So this is like we return a usize and it's like return self context hash key. Yeah. Okay, please. Calc index. He's mad. Why? What's he pissed about? No member named calc index in hashmap test hashmap linear tomb storage. Why not? Oh. Fine. We'll fix that. Oh, size tracking is broken now because this guy's using like fucking parent stuff. God damn it, dude. God damn. Whatever. Fix me size tracking. We'll come back. I don't know how to handle this yet. He doesn't, he is the storage now, so he's happy. These guys need to use linear tomb storage, not self. And then that means everybody who is looking at storage now, he is the storage, so we delete that word. Same down here. We are the storage now, so we're chilling. Just delete, 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 delete. Now does it build? Cannot assign to constant. Yeah. True. Yeah, true. Okay. Now this guy's mad because remove doesn't have self calc index. True. So the storage remove element now needs to take in the key hash and the key or something. I don't know, man. So that he can call calc index himself. Okay. Yup. And then this stuff just lives in here now. And we say, fix me size tracking. How do you get the errors in the log list? Is that new? I don't think so. But I don't remember what I did. I think it's just like a language server thing that you can type. Okay. Please let me not have broken this thing so bad that it's fucked. Okay. Bin hash map test. All tests passed. We're still good. We're still good. We're still alive. Okay, so now the old storage has a different interface now. We'll figure it out. So I guess what we should do here now on the linked list storage, I think the public interface is now different on the storage. It's like get or put, remove element, get. That's kind of an iterator. An iterator. Okay. So get, we'll just start with get or put. That seems like the thing that we need to figure out on linked list storage first. Then we can come back for the rest. Okay, so get or put. How the fuck is this gonna work? So we have a key and we have a key hash. So we start by looking at the key tag, I guess. Right? Surely we need to like mod the key hash with the key storage length. Yes. Okay. Then we have key types at that index. And then, like, what the fuck are we doing here? If it is pointer, we walk the linked list. Right? If it is... if it's key... no, entry... we're chill. And if it's invalid, we convert it to an entry. So this is like convert to valid. This is like return entry. And this is like walked linked list and see if exists, right? That seems pretty reasonable. Seems pretty reasonable. I guess also here it's like, if key doesn't match, convert to linked list. That's kind of what we have to do here. So we look at like, if something, I don't know what yet. Key, the like, you know, stored key is key storage at index, and we know that it's an entry here. If stored key is not equal to key, we need to convert to linked list, right? Otherwise, return found existing true. May I ask, what do you store? I'm not really sure what you mean. Like the key, we're in the linked list, we're storing key value type, where key is kind of more like he might be a pointer to a linked list, or he might be the key itself. And then we also store like which type it is. Okay, so we have if the stored key is equal to the key, then we found it. We get key pointer is key storage. Can we do like this? Then this is stored key like this, and value pointer is just like self value storage like this. Is it array 5 to value or array 5 to linked list? Both, kind of, which is maybe wrong. Right? We kind of like, it means that if the thing is a linked list, this value is kind of wasted. Which is maybe not good. Maybe that's not good. I wonder if it makes sense for us to just always store, like, this maybe should be the value entry or something. This might make our lives a little easier. Hold on. Does this make more sense? Does this make more sense? So, I mean, then why do anything? Like, why do this at all? Why do this at all? What if we just did, like, storage? Linked list entry, like this. Is that just better? And then, like, why are we separating this at all? Like, it was the reason it was split before was because, like, for cache coherency, it's like we know that we're going to be looking at the keys separately than the values. But in this world, I don't really know if that really makes sense as much. This might just be easier. Yeah, I do kind of like this better. Yeah, fuck it. And then this can go back to being valid. Yeah. I kind of like that better, to be honest. I kind of like that better. Always storing a linked list makes more sense. Well, I mean, I was worried about, like, cache coherency as well. But I think here, it's fine. It's fine. Yeah, let's do this. I do like this better. Okay, so now our size is like size of linked list entry size times n plus 1/8 times n, because we can store 8 bits of valid information, or 8 valids per byte. So now this becomes like this again. We then need to do integer math, so we multiply everything by 8. So we do like n times linked list entry plus 1/8 is equal to buff len. We do 8n times, or we do like n times 8 times linked list entry plus 1 is equal to 8 times buff len. So then to do this, to get this back, we get like n is equal to 8 times buff len divided by 8 times linked list entry plus 1. Cool. Cool. So this is a linked list entry. That's the only alignment that we have to worry about. Entry size is size of linked list entry. And then this is bufflen, 8 times bufflen over 8 times entry size plus 1. Okay, cool. Cool. So now we have like storage is of linked list entry, and then we have also the valid storage is a stood dynamic bit set unmanaged. Valid. What do we do on the other one? We resize it, sure. Sure. Okay. Cool. So now our get or put is like, we don't switch on key types anymore. I guess we just check if it's valid. So this is like valid is set on this index. If not is valid, we set it to valid and initialize the linked list. So we say storage at index is equal to key is key, value is undefined, and next is null. Okay. But that's not, yeah, if it's not valid, we do this, and then we return this thing. Bump. So key pointer is storage index key. Value pointer is this stuff. Yeah, fuck it. This is fine. This is fine. And then found existing is false. Okay. So that's kind of the is-valid case. Otherwise, now we're in the valid case. So if it's valid, we need to walk the list. So, so we have like entry is storage index, like, right? So we look at this guy and we say like, while true, I guess while entry is not equal to null, while entry is not equal to null, we defer entry is equal to entry dot next, right? Something like this. Can we do something like entry opt here? Do entry opt entry, and then do like entry opt is equal to entry dot next or something. I don't know, man. We'll see. So then we like have stuff. So we say like if entry key is equal to key, this is it. Okay. So it's like this. Value pointer is this, and found existing is true. Yeah. And then if we make it through this whole thing, then we need to like append an entry to the list. So if entry next is null, then we're fucked. So found existing is false. Good. And then we need to like allocate a new node. So I assume we're gonna have this allocator. And we're gonna like create a linked list entry. And what are we gonna put in here? I guess it's like this. I've been reading what you're saying. I just don't think it's like, I don't really want to think about it right now. I'm also like not really sure I understand what you're saying, but I'm sure we'll figure it out. It's fine. It's fine. Oh, you're giving like too much info. I need to work through the problem myself. I need to work through it myself. I guess this is kind of like the else case here. So this is the new entry, something like this. And key pointer is going to be new entry dot key. You know, value pointer is the new entry value. We need to like assign this entry into the existing linked list. So we have like entry, next is new entry, like this. And then now what? Now what? We have to initialize the key pointer. Or we have to like initialize this thing in general, right? So it's like key is equal to key, value is undefined, and next is null. Okay, easy. Easy. So that should kind of be the whole shebang. Okay? So that's get or put. Iterator is going to, I guess we need get as well, huh? So this thing is going to return, what does it return on the other guy? It returns an entry. So this is probably like, and surely this is going to look very similar to this, right? So this is going to probably go into some so the difference between get and get or put is that this guy's allowed to put a new entry, right? So can we do like get or put impl, right? And here we will say that you like might not be allowed. Allow insert. Right? Something like this. So this is like, we allow insert here. And then that means that this can like, I don't know. Or else unreachable or something. You know, something like this. So if allow insert, he does this stuff. Otherwise, he returns null. Okay. Which means that now on get, we can do... It feels like something's wrong here. It feels like something's wrong. Why or else unreachable? Because in the case where we allow insertion, it should never return null. But like it doesn't, it feels like we're like overloading this API too much, but I don't really have like a better way to do this right now. So I'm just gonna keep it to this way. I don't really like it, but it's fine. It's fine. So this is going to be, and then it's like kind of like this way, like the failure can't happen on get. This is like a fucked API. So it's like catch unreachable. Yeah, this is fucking stupid. I guess what we did before is we had like impl result or something, right? And we had like found, like available, which is gonna have like an entry. Yeah, you could do something like that, but this is fine for now. It's fine. It's fine. If catch unreachable or else return null. There we go. Key pointer is gop, key pointer, value pointer is value pointer. Yeah, there's something wrong here. Fix me. What a bad API. What a bad API. But I think it works, so we'll move on. Okay, so iterating this guy. It means that we're going to go over the whole storage, I guess, and check if things are valid. So we're gonna look at like, if, you know, the key index is greater than the, you know, key storage, whatever the fuck it is, storage len, then we return null. No more iteration to do. And then we have like elem, like this. So this is going to be a pointer to a linked list entry. And what we'll do here is we'll say, I guess this is like an optional pointer. And I guess we start by checking this, right? So we say like if the entry is valid, we like set self elem to elem.next and then return self elem, I think. Maybe we return, no. Let's see. Key pointer is self elem dot, I guess it's like elem dot key. Like this. Okay. So then if this thing is not valid, we set so if we've hit all of our initial points, then we are done, so and then I think we do like self elem is equal to self storage or parent storage at key index, right? So then we like copy the linked list entry out, and I think like this actually. Then we just hit the next iteration of the loop, and that thing is valid, so then we return it. I think that's right. And then the initial element is just null. So on first iteration, we come through here. This is null, so we skip this. Key index is fine. So we end up here. We assign element. We rip back, and then we walk the whole list while this is valid. Increment key. Yeah, I think we're chilling. I think that works. Okay, can we like actually try to compile this thing? right? So let's like set the linked list as our collision resolution. And if, so we say here like if, maybe we switch on the collision resolution. And it's like, if it's open linear or no collision, this is the type we use. Otherwise, we're in linked list and we use linked list storage. Okay. That seems kind of reasonable. And then when we get down here, let's say that we want, a run variant of linked list. And that's going to be something very similar here, except he's going to use linked list as the collision resolution. Oops, like this. Yeah. Okay, so now this is like, if here we need to switch on the config as well. Open linear or this. And then if we're linked list, we need to use the linked list storage. Okay, nice. Num elms here is like this now, true. Key storage length is wrong. This is just storage len, I guess. Cool. What's going on down here? Linked list entry is a pointer here. And then this is like this. We need to store the allocator for later. Okay. Like this. Okay. Now, what's this pissed about? It's like, function with non-void return type is not returning anything. Yeah, it's a pretty good point. So what happens if we get to the end of this? If we get to the end of this, I think this can't happen, to be honest. I think. I'm like 40% on that. This shouldn't happen. We shouldn't be, this is in the storage, the like non-linked list storage, so like we can't be in this storage class if we're using the linked list resolution. What's this bad about? Double pointer, so I guess it's like this? No. Type double pointer to this thing. Oh, it's this thing needs to be like this. Okay. And then he doesn't like return ret there because this guy maybe needs to be called an entry for him to get the type resolution correct. What's this mad about now? No field named remove element in linked list storage. Oh, true. And then no field named iterator in linked list storage. That's confusing. That should exist. Oh, they both say linear storage, like dumbasses. Okay. So this is in linked list storage. We need to write linked list storage here. My bad. And then the other guy is this one, which is that remove element doesn't exist. So, gotta figure out how to make that. Okay. So probably it's gonna be something like this, right? This thing doesn't fail. So let's do something like adding a valid element can fail. I think it's like if you run out of memory. Yes. Yes. So here, I guess we call we want like get element where next pointer. It's tricky. I guess we just kind of, I'm down to just kind of copy paste for a second. because I don't really know how I want to handle this. So if this element is not valid, there's nothing to do. Then we want to look for, we want like to store like the previous entry. Or maybe we want like var next. Yeah. Okay. I think that there's like a special case for if there's one or two elements in the list, probably. Probably. So it's like we need to look at what am I trying to do? I'm trying to block this out. We need like there's like an element here and we're looking at it. And he's pointing to someone, this is like our guy, and then he's pointing to someone else. If we want to remove this thing, we need to make this point to here, right? And if so it's like there's also a special case where there's only one guy on the list, I think. We just delete him. If there's two guys in the list, this is our guy. We set the head to this guy. If there's two in the list and this is our guy, then we delete the next pointer completely. If it's three and our guy's at the end, we delete the next pointer here. Yeah, okay. So it's like, I think it's like if the three cases are like entry head, entry tail, and entry middle, right? So this is set head to entry next. This is clear set previous entry to null. And this is set previous entry to next. But if my entry is the tail, then the next entry will be null. So there's only two cases. It's only two cases because the next will be null and that'll handle the third case. Okay. So, okay, yeah, let's do this. Okay, so if self-storage index dot key is equal to key, self-storage index is now like we like set him to self-storage next. Right? That seems reasonable. So if next, we set him to next, else we set him as invalid. Unset index. And set him to undefined. Okay, so that's kind of like the head case. Right? Yeah. Otherwise, we have previous. Then we make return, right? Probably. Otherwise, we have previous is self-storage index. And entry opt is next. Right. Okay, yes. Yes. And so now we go, while entry opt is available, if entry key is key, we do the removal. And it's just like prev next is equal to entry next. I think. That feels kind of right. That feels kind of right. Maybe? Maybe. Yeah, I'm gonna give it like a solid like 4 to 10 chance of working. Looks like this is just backwards for some fucking reason. And now he's complaining because expected type this thing found a pointer. Wait. Yes. This is a dereference. Yes. And then also I forgot that when we remove the element, we need to put that in like available entries. You know? So like we clear this guy and like push entry. And we should do this here as well. You know? Which means that we need to track that somewhere. Yeah. Yeah, we're starting to chill, dude. We're starting to be there. Okay. Cool. So then where we call the allocator, we'll figure this out in a second. Available. How do we fucking var? This is of linked list entry in it with alloc 0 initial size probably, because like we might not end up with collisions, and then maximum size of like, I don't know. We'll have to figure this out. Configurable, like configurable max freed entries or something. But for now, we'll just put fucking 10,000 in there. I don't give a shit. Available entries is available entries. Yup. Which he doesn't like for some fucking reason. Probably have to write try here. And then this thing wants to be cons, probably. Okay. This is mad because no field name available entries. What do I fucking call it? Available. And then wherever we call the allocator to make one now. I guess this is like a catch unreachable type shit. You know, crash on debug, and on release we just leak the memory. Fuck it, blaze it. This does need to be a pointer, true. Okay. What's this piss about now? Expected type this thing found that thing because this thing also needs to be a pointer now. True. Okay. And so now on get or put impl, this guy needs to be like, available entries. Available entries. So no like pop on here? Do I not have a pop? I have swap remove. Let's make one. Let's make one. I showed you my hash map. Please respond. No. No, thank you. So here we're gonna be like, if self len is equal to 0, return null. We're gonna be like one special case is handled. I'm not convinced. We'll see. We'll hit it if we hit it. If self, then here we're like self, we swap remove. I guess it's literally just like self len minus equals 1. And, const last is equal self get self len minus 1. And then return last. Hype! Hype, so now we can pop off this thing. Or else, this. Yep. Yep. Cool. Cool. So now the available, we like store all of the guys that we don't use anymore. Everyone's happy. That compiles. Shockingly. Shockingly, it compiles. Let's run our test here and try to run it with collision strategy of linked list and see how fucking broken we are. It's gotta be very. Right? It's gotta be. There's no fucking way. Okay, 325 is mad because this guy had const here. Yeah, true, huh? Shh! Const casting away. Shh! Oh. Shh. Nobody said. Don't tell anybody. Don't tell anyone. Of course this doesn't work. Okay, so the question is why? We gotta kind of break this down a little bit. So how do we debug this linked list version? How do we debug this? We have to like, okay, so first of all, also let's make sure that the other versions still work great. Okay, we'll make sure. Okay, so the old version still works fine. This guy's broken as fuck. So I guess we just have to figure out why that is. So I guess probably the simplest thing to do here is like, let's start by iterating this guy and just see what the fuck the values are. Like, can we just see how many fucking things are in here? We'll say, actually, let's not fuck up this test. Can we just run this thing? Let's just look at what we get here. Not this. Populate and print. Yeah, let's just populate and print. Variant. Linked list. Print. Let's see what he does. We've been const casting string literals in C for like 50 years, not the end of the world. Smile, yeah. Shh. But it's bad. Not okay. So we're actually crashing, which is kind of interesting, at 439. So he's saying like lm is lm dot next. Interesting. So that means that either self lm is invalid or lm next is invalid, or doing this this assignment is like broken. So I'm like not entirely sure, so I'm gonna do this just in case. I'm not really sure what the zig rules are here, but I'm paranoid, so we might as well try that. If we still crash, then that's great. That makes me happy. Okay, but and also now we can kind of figure out where the problem is, right? So this means lm dot next. Can we just like GDB this shit? What the fuck is going on here? Why are we freaking out, bro? What's going on? It does look like this element is invalid. A lot of A's in here. That's classic. That's the classic. So that indicates that either the next value is wrong, either like we're not correctly clearing out some of the next things, Or we're like using an invalid element. I'd be curious to see which case this is. Let's just like double check this logic though. So here, when we are trying to put a thing in, we say, if it's not valid, we do this stuff where we just put it directly into self-storage. Great. Otherwise, the storage element is valid. So we look at this guy and we say, yep, we are so valid right now. So valid, baby. And we just look to see, we just iterate, and if we find the key, we're chilling. If we get to the end of the list, then we pop an entry, we assign it, and we put that as the next element. Okay. What about when we like initialize this? This is also good. So it seems to me like it's like pretty impossible for us to assign an element to the linked list without like correctly initializing the guys that we're using, right? So I don't really feel like the bug is there. It feels more like a removal bug, because that's the other option. Okay, so if the element in the storage is not valid, then there's nothing to do. Otherwise, we check the element in storage. So we say next is storage next. Okay. I guess it's possible that we're like setting, do we forget to set this thing as valid? That seems kind of sketchy, right? I feel like we have to do this, no? Okay. I mean, which I don't think should change much, but I think this was a bug. So if it's not valid, we return. Then we look at self-storage key. If it's not valid, set it to valid. Yeah, that's what we just did here. Because we just, like, if it's not valid and we're putting something in. If we allow insert. If is valid. If not allow insert, return null. There we go. So if it's not valid, we set it to valid and assign the stuff, right? Then up here, on removal, if it's not valid, we return. Nothing there. If it is valid, that means that the storage, we check the storage key if it's equal to key, then what is going on here? We say the next element is the next element. If there is a next element, then we reassign our current storage to that next element. Okay, that seems fine. Then we set that thing to undefined and put it back in available entries. Otherwise, we unset valid. So this could be a case where we're ending up with undefined. That like XAAAA shit. Let's run it again. I want to take a look again. I'm a little confused. Oh, assertion failure. On storage remove element. Oh, interesting. I thought we fixed this bug a while ago. I thought we fixed this. But it could be that we're not allowed to use zero-sized, I think that there might just be a bug in our, like, storage class there. So I'm just gonna work around that real quick. Seg fault. Oh, interesting. Why? Because of this, of course. So we're back to the same problem. And the question is why? So where the fuck are we? We're in our iterator. Okay, wait, so maybe our iterator is broken. So we are here. So we're going, if we have an element, then we set this thing. Now, this means that self-elem here is being set to undefined somehow. Okay, that's a key piece of information. Because we're not checking if it's valid. Oopsies. Yeah. We're fucking dummies. Okay, and then I think that's fine. You could get a little more efficient there, but whatever. Okay, wait, that's good. Now the question is does our unit test pass now that we've kind of fixed everything? No, obviously not. Okay, so let's check, I guess, what if we have 100 keys and they're the right keys. So when we print this thing, populate and print. Can we do like num keys is this? Okay. What's going on there? Oopsies. Oops. Variant linked list print. Okay, so we have 100 keys. So that's good. Can we confirm? Okay, wait. That's good. So can we check in our unit test? Let's not check the values. Let's just check that custom val is not equal to null. So do we have the right keys is a question that we should be asking. No. Okay, that's interesting. So can we then say std debug if custom val is equal to null, try std debug print this is missing. What's going on here? Okay. Which she's not saying. Whoa. Oh, interesting. It's actually on initialization he's failing. I didn't even like look at the errors. Has it always been that? Oh, interesting. Okay, wait, hold on. That means that this is probably... Oh, of course, because we have no room for the extra storage. Let's try this. Wait, we're so chilling. Wait, it might have been working this whole time, and like we just didn't allocate enough storage for him to do his thing. Oh, fuck yeah, let's go, baby. Okay, so the linked list mechanism is at the very least, he at the very least has the right answers. The right answers. Now, how fast is he though? Let's compare. Open linear goes to linked list. Oopsies. And linked list. And then can we compare? Stood. Okay, let's make sure that everybody's not printing. Okay, so let's compare stood, open linear, and linked list. Let's see who's the... Oh, let's build in release mode as well. Who's the winner? Who's winner? My assumption would be that our linked list version is shit. That would be my assumption. But you never know till you try. Let's give him a sec. Let's let him think. Okay, so there's our baseline, standard library, our version with the linear stepping, like moving to the next slot is bad. 9.3%. No way! I would never have guessed this. Small thing. If delete next is if next is unneeded because it's checked up. Or yeah, I saw that. Interesting. So this is definitely like almost like the exact opposite of what I would have guessed. Now, I guess this is an unfair comparison because we're allowing more memory use in the linked list version, right? Because like the memory cap here, we're using 8192 for both, but in reality, like in the linear version, that 8192 bytes of memory is being used for both collision storage and non-collision storage. So I'd be curious to see what happens if we drop this. Like, let's say we like half it for the linked list version. Hello, what are we doing here? We're trying to implement a hash map and seeing what happens. We're trying a few different strategies for like collision resolution. Well, I said it was going to be a few. It turns out that we are probably like going to only try one today, but it's fun either way. So we're trying variants where, you know, in one world we have a hash map where if you try to put something in the map and you happen to collide with an entry that's already there, we just put them in the next one. Right? And then if somebody tries to go here, then you just keep moving forwards until you run out of space. Our second thing that we're trying is instead of doing that, we have kind of like initial slots. And if you try to put in here, this guy will go like, oh, I'm already full. Convert this into a pointer, and then we'll store like a linked list of entries over here. Which I would have assumed is shit. This I thought would be real. This is like I thought would be way worse. But the benchmarks are very much saying that that's better, which is surprising. Also surprising is that we're beating the fucking standard library on that one. I guess we should make sure that on the standard library version, we should make sure that we're like ensure total capacity of 100 here or 200. Or else it's probably not a fair comparison. How would you know the index of it in the linked list? You just rip the list. You're just like, oh, look at them all. Okay, let's just see if we made a mistake here. If we pre-jack the capacity of the standard library list, does it start winning again? I would hope so. I would really hope so. Let's give it a sec. So 282, I mean, it's around the same, to be honest. Interesting. That's crazy. Why? Huh. I wonder if it's like due to like maybe like the number of collisions and the kind of like number of entries are probably a relevant thing here, right? If we only have 100 entries, maybe we don't have that many collisions. I would be interested to know what our like load is. I think we lost load tracking when we kind of factored out different storage backends. So I would love to kind of get that shit back. So I guess it's like on get or put in the main guy. Here it's like if ret found existing, if we didn't find existing, we increase size. Okay. Then somewhere, was that the only option? Probably not, right? They would probably need to track the size somewhere else. Probably on like put as well. Right? And then probably, oh no, this is already actually doing the right thing. Nice. And then on remove, we probably have to be like, this guy should return a Boolean if it was removed. And then if this self size minus equals 1. Yep. And then the other guy on here, we need to implement that bool thing on both storage backends. So this guy, if it's not valid, return false. I think this returned something. This did something. This did something. And at the end we return false. For we did nothing. Okay, so now our size tracking should work again. But we're probably also missing this like load stat stuff. Lookup stats. Oh no, this isn't load. This is like collisions, which is like fine. You pre-allocate memory in your hash map, but the standard library doesn't. Yes, it does. Now it does, right? Because we added this. So this should pre-allocate. This should pre-allocate because of this guy. Can we figure out our load? So can we look at like how do we do this? Our storage backend needs to say it's like available space, right? So we need to implement like a length on this thing probably, which we did on this one. On the other storage backend, do we have a length? No, but it's easy to add. Okay. And then do we have max load factor here? We're not using that correctly, but we can at the very least calculate the load. We can add to our hash map like function load or something and at least print it. Okay, so this should be like self storage len. Okay. Would be interesting to run a profiler and see the bottleneck for each of them. Yeah, that would be. I agree. Okay, return. But I don't know. Yeah, I guess it might be interesting. I agree. Let's do that next. Maybe. Maybe. We'll see. Calc load, I guess we'll call this. And then can we do like stud debug print load is this. You are also right that I should have checked the standard library implementation, not just assumed. I assume that it's something about like genericism. I'm sure that there's cases, ours must be worse than other cases. I just don't know what it is yet. It could also be that our load is too low or too high, too low, too low. Could be. Could be. So let's run our thing in a second. Give him a sec, he's thinking. Linked list. Linked list. So our load is like just under 0.7. So if we like give our guy way less space, I assume that means that the load should go up, right? If this is being calculated correctly, which we didn't really verify, but I think it should be. I guess we can at least check the size as well. Let's do that. Size, load. All right, let's do that. Let's do that, because then if the size is calculated correctly, then we know that the load is calculated correctly as well. I think. I think. Yeah, so 127, is that wrong? My gut says that's wrong. I feel like it's supposed to be 100. I think that we've done something fucking stupid. Hold on. Uh, give it a sec. So stood, yeah, size should be 100. So the fact that our size is not 100 is like a big no-no. Big no-no. So what the fuck have we done wrong here? On our public functions, we have down here somewhere. Here we go. Size is 0. On put, we call self get or put, which increases size. Nice. And then on remove, if it found the element, then it decreases the size. So I don't really see how this could be wrong. Okay, linked list. Okay, so yeah, he is not removing stuff that he thinks he should. What about in the other variants, like in open linear? So he is not. Okay, so we are failing to notify that we removed something that we removed, or we're actually not removing something that we were supposed to. But the answer are the unit test is working, which indicates that we have the right contents of the list, but we're probably just not flagging this correctly. So if this thing is not valid, we return false. I mean, it seems pretty fucking clear cut, no? If we found the key, we return. If they found the key, we return true. So how could we possibly be wrong here? Interesting. Interesting. What are you using for the hash function? Just whatever the standard library uses. I think it's WY hash or something. This is scary. The fact that this is wrong is a problem. I just can't find where that would be. So remove element. I mean, this is wrong in the general case. Why not use the standard library? Because I want like a different storage format, kind of. I don't like the idea. I want like a not growable hash map, or a growable hash map that doesn't ever like lose storage, because our allocators don't support free. Yeah, what the fuck is going on here? I guess we can kind of at least bisect the problem like this by hitting if true unreachables on the false sides. So this is at 370. So we're getting through the whole list here and not finding anything. Why though? Why? And how the fuck? How the fuck is the iterator returning 100 entries? Is it? Num keys 100. Okay, so let's just double check that num keys is in fact 100. So let's go back and fix these unreachables. What the fuck? Oops. Oops. I need to print. Print, please. Maybe it's wrong and I just didn't notice. Oh, yeah, num key is 100. So how is my size 127, but my num keys is 100? We must not be decrementing the size somewhere. Somewhere. What the fuck? Or we're incrementing it too much on the other side when we put stuff in. Okay, what if we just don't decrement this? Then it should be 200 if I remember correctly. I think we put in 200 things and then remove 100. So this should say 219 is confusing. 219 is very confusing. That would at least somewhat explain something. So that indicates that, like, we're returning that we didn't find existing too many times. Right? Because, like, when we call populate hash map in main, or hash map test, I should say, this guy is, he has num keys 100. He allocates double that. And he tries to put these keys in, he tries to, like, initialize these guys with 0, then remove a bunch of guys. So I guess it might be interesting to, like, print the size here? No. So this is only calling put at this point. Yeah, so let's try that. After put, we have this much. And let's, like, try to, like, get the standard library API so that we can call this on everybody without problems. So I guess what I'm expecting to see here is after put 200. So that makes sense. So it's like after this part, then after remove, what's the size? So let's go back to the linked list guy here, and wherever, like, the size decrement was, let's bring this back. So I'm hoping to see 200, 100, I guess. 108 after remove. And then I guess it's growing again? I guess this should never be happening. Because here we should only be looking at keys that already exist, right? So I guess we should be like assert. This should always be true. Because we've already initialized these guys with 0 back here, right? Okay. So first let's run the standard library version. And yeah, so after that, that is correct, right? So it's like 200, 100, 100. And if we run the linked list version, we're falling over. So that means that, like, this getter put is just not implemented correctly. It can't be. It means that we have to be walking this list wrong or setting the return value of found existing incorrectly. So here we did not find, it was not valid, so found existing false. If key equals key, found existing true. if we got to the end of the list, then we create a new one and insert it into the list. It's gotta be like list management is bugged in some way. Right? This is the only, this case. So we start with looking at like this, the built-in storage. This thing is valid at this point. Okay. Geez. It's what's really confusing to me. What's really confusing to me is that like the values are correct? No? In this, maybe I got confused. So here we're using the linked list variant. We populate the hash map with 105,000. So maybe that's different. Maybe that's different. We iterate our guys. Oh no, because our iterator is working correctly. And so we iterate everything, we compare the values with what's in the hash map. Okay? Okay, wait. That's a clue. Oh, wait. Oh, okay. Wait. Let's go back. Yeah, so this test is passing despite the fact that our count is too high, right? Which means that, like, all of the things that are being returned by our iterator are the values that match the correct answer. Which means that it must be something about the valid tracking. I think. I guess we just have to figure out what the difference is between these guys. No, because, okay, this guy goes and he says, if valid is set, we use this guy. Then we walk his list. Simple. Until our element is null. This guy says, check if he's valid. Okay. Then walk the list. Are we forgetting to, like, set the entry's next pointer or something? I wonder if it's something like that, where we're not linking it correctly. Here, entry next. Did we forget to do an entry next here? No, because it should be null. If it's the first, if we're inserting into an empty list, it has to be null. Set valid. If it is valid, valid's already set. Huh. Interesting. So we do know that it's one of the found existing false cases, right? We do know that. So can we... I wonder if there's, like, a way to leverage that information. Like, we could... We know that on put, we can set a global that says, like, allow put. Yeah. Yeah, let's do this for now. Okay. Then we can have, like, up here, we can have some global. Allow put is false. And then if we are in our get or put implementation, we can be like, if global allow put unreachable on both of these guys. And we can see which one of these is freaking the fuck out. So 391, it's here. So we're ending up with invalid elements at the head that should be valid. So does valid ever get unset? Here. Is that the only place? Yes. So this is happening if next, if we have a next value. Oh, is this wrong? I don't think so. So we like copy the next element back into our head, then delete that entry, and that's fine. Because we should have been the only guy pointing to this. And then here, if we don't have a next value, then there's nothing to copy into our guy. Yeah, I don't see a world where this is wrong. I don't understand. I do not understand. Okay, so let's just do this for a second. Just for a second. This should just, like, break all sorts of shit, right? But oops. Linked list. Yeah, so that makes sense that that's broken. Which is not helpful to me. Not helpful. So I guess this could be happening if our linked list dies too early. Previous next is entry next here. Yeah, I'm not seeing it. I'm not seeing it. What about this? What's going on here? So if we are trying to remove an element from the list, we say, hey, entry key is equal to key. That's the fucking success case. Don't you have too many elements, which means you don't unset values in places? I agree. Wait, maybe I don't agree? I think that I'm unsetting valid too often. Which means that, like, on the next insert, it seems like we're supposed to pre-jack the list with all of our available keys. And then what's happening is, like, later, we are, like, trying to get those keys again, and we're failing to. We're like, hey, this thing that's supposed to be in there isn't fucking there. Which is confusing. right? And it's like it's in this case where we're like seeing this thing is not a valid head of the list when it should be, which means that we're unsetting too much on removal, is what like kind of how it feels. Like we're removing too much or something. Or like maybe I wouldn't be like super shocked if we're like somehow managing to flip our like key and key hash here. Although I guess in that scenario we would get like compile errors because the types wouldn't match. But we also see like after removal that there's too many elements, which is also weird. That's also weird. So it's like both that there are too many elements and not enough elements at the same time. Do you have to set valid after appending to the end of the list? I think that the valid should only be set when putting in at the very beginning. I think. But maybe we need to unset it when removing the last element. And maybe we're not doing that. What's going on down here? That's the iterator. It's also so weird that when we walk the list in the iterator, we get the right amount of numbers. That's also really fucking weird. Oh, but maybe that's only at the end. After it's resolved itself. Maybe. So you're saying, do I also have to set valid after appending to the end? I feel like no. It really feels like it's only here. Okay, so the fact we still have that problem where we are failing. We're flagging that there are things that we tried to remove that we think we're removing something that should be in the list and it's not getting removed, right? I think that's still a thing that's happening. Every single element that we're moving should be in the list already. So those two things are probably related. Variant linked list. Yeah, so we are. Please explain why you need a valid list at all. It's because like the head of these lists are stored in like contiguous storage here, and initially these guys are all set to like undefined. I guess, yeah, I think that the allocator does that for us. Okay. Yeah, I'm really missing something obvious here. I just can't quite find it. This is the classic bug hunting. Okay, so we find a valid entry. We walk to the end of the list and we never find our key. Why would that be the case? Why would that be the case? Can we do something like removing key? Let's like write down the key we're moving. Just to give myself some info. And then we'll also say inserting key on put. Or something. Are you maybe skipping ahead? It just feels like it's gotta be, right? So here, when we're trying to remove this guy, he's definitely in there. And we're definitely only seeing this guy here and here. It could be if we're removing the wrong element, I guess. Yeah, I guess that's possible. Okay, so removing key, hash this, or index. Maybe we're somehow fucking this up? Let's see. Oopsies. Build first. Okay, so index 17. Index 17. So he is right. Now I guess the question becomes, does this guy who's removing at 17 fuck some shit up for us? Right? That seems pretty likely. Right? So let's say on removal, we'll say cleared list at index 17. Can you hook up a debugger? I think that this is the type of bug where a debugger doesn't really help me, because I need to see like history of things that are happening. You know? Here we'll say updated head, and here we'll say remove from middle of list. I'm assuming that we're going to see that we cleared the list when we shouldn't have. That's what I'm expecting to see here. So here at index 17, we did remove from middle of list here. Okay. Then here we don't find anything. Oh yeah, because we have the list still. Which makes me think, can we look at remove from middle of list? Can we look at this, like the 3 keys that are related here? Maybe that's information that we can use. So prev key, entry key, entry next key. That might crash. It might. Yeah, okay. If next key is entry next, if entry next entry and key, or else else -1 or something like that. Okay, so when we remove from index 17, we have these 3 numbers, which this number, wait, is not this. 6741. So none of these are that guy, actually. Okay. So that's interesting in some way. I don't know how yet. I would also be interested to look at the whole list or something. Yeah, there's something interesting there. I can't place it. I guess, can we also, if index is equal to 17, return false. I just want to see what happens in that case. Oh, I'm a fucking idiot. Of course that doesn't help. If I want the key, let's look at that first key that we're removing at index 17 and see if that changes the behavior at all. If key is equal to this, return false. We didn't remove it. So now the second iteration of index 17, this actually works. 6741. So that's interesting. By removing the previous middle of list thing, this guy now succeeds. So it's gotta be related to this. I just can't figure out how. So entry opt is a pointer to self storage next. No, it's a pointer to a linked list entry. Cool. We say, yo, my previous entry is the head of the list. My current entry is the next element. Do I not update previous? Oh my fucking god, dude, yeah. Good fucking eye. Yeah, that's gotta be it, right? That's gotta be it. So we're always fucking nuking the first one? Yeah. Good fucking eye, dude. Yeah. God damn, I've done that so many times. That's a fucking classic, my dude. Okay. So now can we go back to let's get rid of these prints because they're killing us. Updated, like, oh, I guess those are fine. After remove 100, yeah, okay. Fuck me, man. Linked lists are hard. I'll say it. So why was it working at all before? Because so on removal we just fucked up the list, but then we like corrected it on insertion again. So it was like, okay. That's funny. Okay. Let's compare our three variants again. Boop. I don't even remember like how we ended up here anymore. I just got like because this problem just got so fucking broken. But now that our thing works. Oh, that's interesting. Now our guy is no longer faster than the standard library. What? So before we were somehow getting the right answer and being faster than the standard library, probably because we didn't have elements in the list that we had to walk anymore or something. And now we're not anymore. How interesting. How interesting. Okay. But our linked list version is still faster than our other. Oh, did we change the capacity? Maybe we did drop the capacity a little bit. Right, we were looking at load factor. That's why we were doing this. We were looking at load. I remember now. We wanted to see if our thing was only faster because the load was too good. I remember. So we were trying to print the size and the load here. Ah, yes. So we run this guy. The load is 1.19 here. Really bad. But if we increase the size of this guy again to like 1 page. I remember. Give it a sec. He's thinking. Okay. So now our load is really low, 0.6 versus like a 1.1, right? If as long as we give him enough space, we're chilling. So probably now we'll be faster again. And I guess it probably makes sense that the speed improvement is coming from the fact that we have a fixed capacity buffer. Right? So like here, like we're probably just skipping a bunch of stuff that the standard library has to do because of the fact that we just never expand. And so like as long as we pre-size our load to be like about our list size to be like good enough, then we're kind of chilling. That's cool. And it's also cool. What's our load on the open linear version? I want to compare. Because maybe this is an unfair comparison somehow. Maybe if the load of this guy was also around 0.6, it would be cool. Maybe he'd be faster. Maybe. No, his load is really fucking low. His load's 0.2, and yet it's still slower. That's funny. Yeah, that's interesting. So even with like a really low load on the like version of this thing where he just kind of like moves forward, it's still like significantly worse than the linked list version. Neat. The chain map beat the OA one? Yeah, by like a significant margin. That's like very surprising to me. It's cool how like your expectations don't necessarily match reality at all. It's funny too because like arguably this implementation is easier. I know we struggled a lot today, but I think that if we had like better types kind of backing it, it would have been easier. That's really cool, really interesting. Okay, cool. I mean, we've gone over time today. I really expected to do more today. I wanted to try some other mechanisms as well, but we really like fell over on this one. So classic programming. But yeah, this is really like eye opening in some way. Cool. All right. Thanks for watching, guys. If you like what we saw, we stream most days 12:30 Pacific time to 4 o'clock Pacific time. It is 4:20 now. Blaze it. Bless up. Shut up. Shut up. Shut up. I can't stop myself. I have to say it. So anywhere between 4 hours ago and now-ish is when you should expect to see us live. If you can't catch us live, there's a YouTube link in the Twitch description where stuff that's like YouTube algorithm friendly ends up. So this will end up there. I think this is a good YouTube friendly video, but some stuff is not, right? And so if you want access to like kind of all of the VODs, there is a Patreon and a YouTube member segment, as well as like VODs go up on Twitch if you are subbed. So if you want to support the stream, because this stream will end when I need to get a job because I have no more money, you can support on those places and get VODs, the remaining VODs that aren't YouTube friendly. So please consider, but obviously no pressure. Otherwise, YouTube, peace out, and Twitch, let's find someone to raid.